To begin with the simple stress, we will consider two bars of equal length that are suspended from a common support. So we have here bar 1 and bar 2. Bar 1 has a cross-sectional area of 10 square millimeter, and bar 2 has a cross-sectional area of 1000 square millimeter, and bar 1 has a maximum axial loads of 500 Newton, and bar 2 has 5000 Newton. In this instant, we cannot tell which material is stronger unless we will solve for the stress or the load capacity per unit area. So for the bar 1, the stress is equal to the force, which is 500 Newton, divided by the cross-sectional area, which is 10 square millimeter. So it is equal to 50 Newton per square millimeter. While for bar 2, it has a unit strength of 5000 Newton divided by 1000 square millimeter, which is equal now to 5 Newton per square millimeter. Thus, it shows here that the material of bar 1 is 10 times as strong as the material of the bar 2. For our example number 1, a composite bar consists of an aluminum section rigidly fastened between a bronze section and a steel section is shown. Axial loads are applied at the section or at the positions indicated. Determine the stress in each section. So to calculate the stress, we must first determine the axial load in each section by passing an imaginary line or by drawing the free body diagram. So for the bronze, we will take the summation of forces of horizontal is equal to 0, right direction as positive. So force B minus 17,000 Newton is equal to 0. So our force B now is equal to 17,000 Newton. So the stress will now be equal to the axial force divided by the cross-sectional area, which is 775 square millimeter. So for the stress in the bronze section is now equal to 21.94 Newton per square millimeter, or 21.94 megapascal. So how did I arrive into megapascal? So Pascal is equal to Newton per square meter, and mega is equal to times 10 raised to 6, then Pascal, Newton per square millimeter. So we will just convert it into Newton per square millimeter by multiplying it with 1 over 1000 square millimeter. So in 1 meter there's 1000 square millimeter. So converting it into megapascal, therefore in 1 megapascal it is equal to 1 Newton per square millimeter. That's how I arrived on 21.94 megapascal. So to continue, for the section or for the aluminum section, again drawing the free body diagram by passing a line to reflect the actual load for the aluminum section. So taking the summation of the forces horizontal, write direction as positive, so negative 17,000 Newton plus 40,000 Newton minus the force at the aluminum section is equal to 0. Therefore, the force in the aluminum section is equal to 23,000 Newton. And solving for the stress, the cross-sectional area for the aluminum is equal to 1,200 square millimeter. So substituting the values, therefore our stress at the aluminum section is equal to 19.17 megapascal. And then for the last section, same step, we will pass an imaginary line at the steel section. Taking the summation of forces horizontal is equal to 0. Right direction as positive, so negative 17,000 plus 40,000 plus 9,000 Newton minus the force or the actual load in the steel section. Therefore, the actual load is equal to 32,000 Newton. So the stress would now be equal to 32,000 divided by the cross-sectional area, which is 1,000 square millimeter. So it is equal to 32 megapascal. So whether you start on the steel section or on the bronze section, you will be arriving the same answer. For problem number 2, for the truss shown, determine the stress in members AC and BD. The cross-sectional area of each member is 900 square millimeter. To begin with, we will first determine the forces in each support. Located in support A, the roller, and then the hinge at support H. We will determine it by having our summation of moment at H is equal to 0, clockwise positive. So the vertical force at the roller A multiplied by 16 minus 30 times 12 minus 70 times 4 is equal to 0. So AB now is equal to 40 kilonewton. And then taking the summation of forces, of vertical forces, is equal to 0, upward positive. So HV plus 40 kilonewton minus 30 kilonewton minus 70 kilonewton is equal to 0. Therefore, our vertical force at support H is equal to 60 kilonewton. And then we will consider the horizontal force at the H support as 0 kilonewton because there is no any other horizontal forces acting on the diagram. So just consider it as 0 kilonewton. Our next step is to determine the internal forces acting on the member AB and AC. We will take the joint A. We will draw the free body diagram of all the forces acting at joint A. We will assume that there is a compressive load at member AB and a tensile load at member AC. So we have a slope here, the slope, 3 vertical, 4 horizontal. So by taking the summation of forces, vertical is equal to 0, upward positive. 40 kilonewton minus 3 all over 5 of force AB is equal to 0. Therefore, the internal force along member AB is equal to 66.67 kilonewton, and our assumed compressive force is true. And then we will take the summation of the forces horizontal is equal to 0. So negative 4 all over 5 of 66.67 plus our force AC, our assumed tensile load AC. So I'll just write here below. So again, negative 4 over 5 of force AB, which is 66.67, is equal to 0. Therefore, our force at AC is equal to 53.34 kilonewton in tension. And our next step is to determine now the stress at the member AC. So our load is 53.34 times 10 raised to 3 Newton divided by the cross-sectional area, which is 900 square millimeter. Therefore, our stress at member AC is equal to 59.27 megapascal. And to continue it, we will determine now the forces or the force acting on the member BD by considering joint B. So again, we will draw the free body diagram at joint B. So force AB is in tension. No, it's in compression rather, as we have solved on the first part or in the joint A. Then how did I arrive at the 30 kilonewton? So you just take the joint C, taking the free body diagram at joint C. So member BC has a tensile load of 30 kilonewton. So taking the summation of forces vertical is equal to 0. Upward positive, so for FBE, 3 all over 5 of force BE is equal to 0. Therefore, force PE now is equal to 16.67 kilonewton in tension. So our assumed direction is correct. So next we will take the summation of forces horizontal. Right direction positive, so negative force BD plus 4 all over 5 of force AB or force BE, rather 16.67 plus 4 over 5 of the force AB, so 66.67. Therefore, our force BD is now equal to 66.67 kilonewton in compression. So we are now ready to solve for the stress for a member BD by taking the force BD divided by the area of the member BD. So the cross-sectional area of member BD is equal to 900 square millimeter. Therefore, the stress in member BD is equal to 74.08 megapascal. For example number 3, the block of weight W hangs from the pin at A. The bars AB and AC are pinned to the support at B and C. The areas are 800 square millimeter for AB and 400 square millimeter for AC. Neglecting the weights of the bars, determine the maximum safe value of W if the stress in AB is limited to 110 megapascal and that in AC is 120 megapascal. So we will first draw the free body diagram. We have W and then the forces acting on AC and AB. So AC is 60 degrees from the horizontal and AB is 40 degrees. So our next step is to take the summation of forces vertical into 0. So the forces AB sine 40 plus force AC sine 60 minus W is equal to 0. So we will just take the force AB and force AC in terms of W. Next is to determine forces horizontal is equal to 0, right direction positive. So force AC cosine 60 minus force AB cosine 40 is equal to 0. Therefore, force AC is equal to 1.53 of force AB. So equating equation 1 and equation 2, therefore force AB is now equal to 0.51 W, and then for force AC we will make it in terms of W. Force AC is 0.78 of W. Now we are ready to determine the weight. So substituting stress AB into 110 Newton per square millimeter, and then our area in AB is 800 square millimeter, and then force AB 0.51 of W. Therefore, our weight is equal to 172,549 Newton, or 172.55 kilonewton. And then for section AC, our stress in AC is 120 megapascal, and then force at AC is 0.78 of the weight, and then our area is 400 square millimeter. Therefore, our weight is equal to 61,538 Newton, or 61.54 kilo Newton. We will be considering the smaller value, 61.54 kilonewton, because if you consider the larger one, the bar may fail. So the safest value of W is 61.54 kilonewton. A hollow steel tube with an inside diameter of 100 mm must carry a tensile load of 400 kN. Determine the outside diameter of the tube if the stress is limited to 120 MPa. So we have here a hollow steel tube with an inside diameter of 100 mm and a tensile load of 400 kN. We will determine the outside diameter of the steel tube if the stress is limited to 120 MPa. So we will just substitute the values here. 120 megapascal or 120 Newton per square millimeter is equal to the tensile load, which is 400,000 Newton, divided by the area that is covered on this part. Since this is a hollow steel tube, we'll be considering the difference of the area covering the outside diameter and the area covering the inside diameter. Therefore, our outside diameter is equal to 119.35 millimeter. For example number 5, a homogeneous 800 kg bar AB is supported at either end by a cable as shown. Calculate the smallest area of each cable if the stress is not to exceed 90 megapascal in bronze and 120 megapascal in steel. So again, our first step here is to draw the free body diagram. We have the bar AB on the cables located at the ends. So the weight of the bar is 800 kilogram, or the mass of the bar is 800 kilograms. So we will convert it into weight by multiplying it with the gravity, which is 9.81 meter per square seconds. Therefore, the weight of the bar is equal to 7,848 Newton. And then since the cable are located at each end or at both ends, the forces in the bar A and bar B, or the bronze and steel, is just equal to 7,848 divided by the 2, or just the half of the weight of the bar. Therefore, for the stress at the bronze cable is equal to 90 megapascal, and the stress in the steel cable is 120 megapascal. So to determine the area of the bronze cable, we'll just substitute the values here. Therefore, the area at the bronze cable is equal to 43.6 square millimeter. And then for the steel, our stress at steel is 120 megapascal, and then our force at the steel cable is 3,924 Newton. Therefore, the area of steel is equal to 32.7 square millimeter. For example number 6, a rod is composed of an aluminum section rigidly attached between steel and bronze sections. Axial loads are applied at the positions indicated. If P is equal to 3,000 pounds and the cross-sectional area of the rod is 0.5 square inches, determine the stress in each section. So just like the first problem, we will just pass imaginary lines in each section, but here it is rigidly fixed, so there is a moment, vertical and horizontal section acting on the support, and there are forces or external forces with P is equal to 3,000 pounds, and for P is equal to 12,000 pounds. So we will start by passing section at the leftmost part, or the steel section. So having the free body diagram of the first section, the internal force acting on the steel can be determined through having the summation of forces horizontal is equal to 0, right direction positive. Therefore, the force at the steel section is equal to 12,000 pounds. And then the stress at the steel section is equal to 12,000 pounds divided by the cross-sectional area, which is 0.5 square inches. Therefore, it is equal to 24,000 pounds per inches squared. So PSI is pounds per inches square. And then doing the same procedure on the next section, the aluminum section, drawing the free body diagram. Taking the summation of forces is equal to 0, right direction as positive. Therefore, our force at the aluminum section is also equal to 12,000 pounds. Therefore, the stress at the aluminum section is equal to 24,000 pounds per inches square. And then for the last part, for the bronze area, same procedure also. It has an external load of 3,000 pounds acting on the aluminum section. So taking the summation of forces horizontal is equal to 0, right direction positive. Therefore, the internal force acting on the bronze section is equal to 9,000 pounds. And then the stress is equal to 9,000 divided by 0.5 square inches. Therefore, it is equal to 18,000 pounds per inches. So for the last example, for simple stress, determine the cross-sectional area of members AG, BC, and CE for the truss shown. The stresses are not to exceed 20 kilopounds per inches square in tension or 14 kilopounds per inches in compression. A reduced stress in compression is specified to reduce the danger of buckling. So here is the diagram. So our first step is to determine the forces acting on each support. So at support D, we have a roller, and then at support A, we have hinge support. So taking the summation of moment at A is equal to 0, clockwise positive, so negative D, and then the moment arm is 18 plus 25 multiplied by the moment arm 8 plus 40 multiplied by force equal to 0. Therefore, the force acting on support D is 20 kilo pounds. And then taking the summation of forces is equal to 0. Our summation of forces horizontal is equal to 0. Right direction is positive. So AH minus DH is equal to 20, and then our DH is equal to 20 kilopounds. Therefore, our AH is also equal to 20 kilopounds. And then the summation of forces vertical is equal to 0, upward positive. We have the vertical force at A is equal to 65 kilopounds. And now we are ready to determine the internal forces on each member. So at joint A, drawing the free body diagram of all the forces acting at joint A, we will assume that member AB is in compression and member AG is in compression also. And then our slope here is 4, 6, and then the hypotenuse is equal to 2 square root of 13. So we will determine the forces by having the summation of forces vertical is equal to 0, upward positive. So 65 minus 6 all over 2 square root of 13 of force AB is equal to 0. Therefore, force AB is now equal to 78.12 kilopounds. And then summation of forces horizontal is equal to 0. Our force AB is in compression. Our assumed direction is correct. So taking the summation of forces horizontal is equal to 0. So 20 minus force AG minus 4, 2 square root of 13 of force AB, which is 78.12 kilopounds. Is equal to 0. Therefore, force AG is equal to 23.33 kilopounds. Our assumed direction is wrong. So we will change the direction. It must be in tension. So we just change the direction or change the orientation because FAG is negative 23.33. So the stress at AG is equal to 2 20 kilopounds per inches square if it is in tension. So force AG is in tension. We will use 20 KSI. And our force AG is 23.33 times 10 raised to 3 pounds. Therefore, our area at member AG is equal to 1.17 inches squared. So again, kips is kilo pounds, and then KSI is kilo pounds per inches square. So kindly take note of that. It is in English system. And then next step is to determine the forces acting on member CE and member BC. So taking the joint D, drawing all the forces acting on joint D, force DE, and for the force DC we will assume that it is in compression, and the slope is 4/6 and then 2 is square root of 13. Therefore, taking the summation of forces horizontal is equal to 0, right direction as positive, negative 20 plus 4 all over 2 square root of 13 of force DC is equal to 0. Therefore, force DC is equal to 36.06 kilopounds. And then taking the summation of forces vertical is equal to 0, upward positive. So 36.06 of 6 divided by 2 square root of 13 minus force DE is equal to 0. Therefore, force DE is equal to 30 kilopounds. And our next step is to pass an imaginary line between member BC, CF, and FE to determine the value of a member BC. So we will we will solve the internal forces acting on the members. So to begin, we will start by taking the summation of moment at joint F is equal to 0, clockwise positive. So negative 20. The moment arm is 12. And then the vertical force acting on member BC. So 6 force BC multiplied by 6 divided by 2 is square root of 13 is equal to 0. No, the moment arm is 4, then equal to 0. Therefore, force BC is equal to force BC is equal to 72.11 kilopounds. Force BC is equal to 72.11 kilopounds. And then taking the summation of moment at C is equal to 0, clockwise positive. So the vertical forces of member EF, the moment arm is 4, minus 20 of moment arm again is 6. Moment arm is 6 is equal to 0. Therefore, the force acting on member EF is equal to (36.06 kilopounds). And we are now ready to determine the areas. Force, so at joint E, drawing the free body diagram at joint E by reflecting all the forces acting on it. So force EF, by the way, is in tension, and then force BC is in compression. So I assume that the force CE is in compression. Therefore, taking the summation of forces horizontal is equal to 0. Right direction as positive. So force CE minus 36.06, and then the slope is 4 all over 2 square root of 13 is equal to 0. Therefore, force CE is equal to 20 kilopounds. And it is in compression. So we're now ready to solve for the areas in member BC and member CE. So in member CE, since it is in compression, the stress is equal to 14 kilopounds per inches square. So 14 times 10 raised to 3 pounds per inches square is equal to 20 times 10 raised to 3 pounds divided by the area in CE. Therefore, the area in CE is equal to 1.43 square inches. And then for the member BC, so same procedure. Our stress in member BC is also equal to 14 times 10 raised to 3 since it is in compression. And then our force BC a while ago is equal to 72.11 times 10 raised to 3 pounds divided by area of BC. So the cross-sectional of member BC would now be equal to 5.15 square